Okay. So I'm going to start by talking about anaerobic cellular respiration by challenging you with questions. Now you're gonna pick up on something. Number one, any question that I'm about to ask you, it would be an awesome question on the third exam, not the next one. The next one is unit 3 and 4. On the third exam. Okay. And the other thing you need to pick up on is the answers to all of my questions. And you'll see this, because I'll leave this up. The answers to all of my questions are going to be on the slide right here. Except maybe when I ask you something about eukaryotic cellular respiration, because that's not a eukaryote, this is prokaryote. But I'm going to challenge you with that one too, to see how many of you know those answers as well. I'm trying to stress something. If you know the flow chart, you will know most of the answers on the exam. That's why I'm pushing this. So let's give it a try. Glucose, this is anaerobic cellular respiration. Glucose comes into the cell. How many carbons does glucose have? 6. It's on the screen. You're going to notice something. It's exactly the same event as aerobic cellular respiration. The only difference is at the end, right here. That's it. Instead of oxygen, anaerobic cellular respiration will use one of these 3. So instead of oxygen, it's either sulfate, carbonate, or nitrate. We're going to talk about nitrate. Why? Because you guys did the nitrate reduction test. You did those tubes that you set up. You haven't looked at them yet. But you're going to look at them on Tuesday. And that's why that's another reason why I don't want to challenge you yet. Because I'm not done with the story. With the nitrate. The nitrate will be completely done with it when we do the lab on Tuesday. Then I can sleep at night and test you on it. Okay? So we're going to talk about what if nitrate is the final electron acceptor for anaerobic respiration. What will happen? Well, it's going to receive the electrons at the end. That's the only difference. If it was oxygen, it would be oxygen, and what will it turn into if it was oxygen? It turns into water. It picks up electrons and hydrogen and becomes water. This guy is going to pick up electrons and become something else. We'll talk about it on Tuesday. So that's the only difference. But everything else is the same. So let's give it a try. Glucose is a 6-carbon molecule. It enters the cell. The first event of glycolysis, which is the breakdown of sugar. Glycolysis. Breakdown of sugar. The first event, does it require energy or does it produce energy? It requires energy. And because it requires energy, what is the 4 or 5 or 6 reactions collectively, what are they called? Energy investment phase. Very good. Because you're putting in energy in the form of ATP. How many? It's on the screen. The power of knowing this chart. All the answers to my question, they're right there. 6 carbon sugar, 2 ATPs being used. That's why it's called the energy investment phase. This is breaking down the sugar. Yeah, that's why it's called glycolysis. Where is it happening? Cytoplasm of bacteria, right? Where is it happening in your cells, eukaryotes? Also cytoplasm. Very good. What do I end up with is 2 G3Ps. Do you agree? Good. The next step will take G3P and will produce pyruvate, right? Now, will I lose carbon?
No.
No carbon being lost. Good. Will I lose electrons and hydrogen? Yeah, but will I lose them, or will I load them on a truck? I'm going to load them on a truck. So the electrons and the hydrogen will be loaded on this truck. Am I right? The oxidized form is the NAD plus. So what is this form called?
Reduced.
The reduced. Why is it reduced? Because it got the electrons and the hydrogen. Very good. Each G3P changing to become pyruvate makes NADH, right? But I have two G3Ps, so I will have two NADHs. Two G3Ps, two pyruvates, two NADHs. Am I right? Good. In the second phase of this, is there energy being produced? Yes. In what form?
SLP.
No. What is the molecule? ATP. By what process?
Substrate level.
Substrate level phosphorylation. How many ATPs?
4.
4. The net gain is how many?
2.
2. Look what I'm doing. I'm giving you a preview of the exam. That's how the questions are going to come at you. How many are made? 4. But what's the net gain? 2. You got to watch out for that. By what process? SLP. Location? Cytoplasm. There's glycolysis right there. It's not that bad. It really isn't that bad. So at the end of glycolysis, I have 2 pyruvates, am I right? I have 2 NADHs, am I right? I have a net gain of 2 ATPs made by substrate level phosphorylation happening in the cytoplasm. Good. Now watch this. At the point of pyruvate, a decision has to be made. We know what has to happen to pyruvate. You have to remove it. You have to remove pyruvate to prevent negative feedback inhibition. That's one main goal, is to get rid of pyruvate. The reason behind it is because you want to keep this thing moving. If pyruvate builds up, it's going to shut this down, and you're not going to survive that. So we got to get rid of pyruvate. Now, if this was a facultative anaerobe, let's say it's a facultative anaerobe, the first thing it's going to look for is, do I have oxygen? Because that's what it prefers. Remember that? A facultative anaerobe prefers oxygen. If I have oxygen, that's what I'm going to use to make a maximum yield of 38 ATPs per glucose, because I'm more efficient with the oxygen. A facultative anaerobe can also say, well, I don't have oxygen. Do I have nitrate? Yeah. Then I'm going to do anaerobic cellular respiration. It'll be exactly the same event, except at the end it's not oxygen, it's nitrate. What if it doesn't have either one? It doesn't have oxygen, and it doesn't have any one of these. Now what? Fermentation. It's going to get rid of the pyruvate, one way or the other. I'll prefer with oxygen. But if not, I have a backup. And if not, I have a backup to the backup. But I got to get rid of the pyruvate to keep glycolysis moving. Very good. So we're going to do that first. We're going to say, yes, I have nitrate. Now, if this is a facultative anaerobe, it has a choice. Well, what if this is an obligate anaerobe? Will an obligate anaerobe look for oxygen?
No.
Absolutely not, because oxygen would kill it. So an obligate anaerobe will not, I don't want oxygen. I would look either for one of these or do what? Fermentation. Very good. What if I'm an aerotolerant? Will I look for oxygen? Will I look for one of these? What can I only do? There it is. Be careful with this one. Aerotolerants. They only ferment. That's it. No other choice. So they're going to go to pyruvate automatically through fermentation. They're not even going to look back. Do I have this? I don't care if I have it or not, because I can't use it anyways. All right, so aerotolerant, they will only ferment. Okay. Now, in this situation here, in my example here, we're gonna say, yes, we have nitrate. Sounds good? So we can keep it moving. So pyruvate is made. Do I have nitrate? Yes. Then I'm gonna oxidize the pyruvate. I'm gonna break down the pyruvate into acetyl-CoA. How? By losing a carbon. The pyruvate is 3 carbons, the acetyl-CoA is 2 carbons. So you're losing a carbon in the form of CO2. And every time you lose a carbon, you make NADH. So why do we have 2 carbons? Because we have 2 pyruvates. The power of the flowchart. You gotta start working on the flowchart, no doubt about it. Okay, so at the end of pyruvate oxidation, the 2 acetyl-CoAs are now available for the Krebs cycle. I have 2 CO2s. How are these CO2s leaving the cell? Which kind of diffusion? Simple diffusion. They're gas. They're non-charged and small. So they're gonna go right through the cell membrane. I'm gone. Now, if this is bacteria, they're just right outside here is the environment, right? But if it's you, it has to be picked up by your red blood cells or dissolved in your blood for delivery to your lungs so you can go and expel it out. So we have to breathe it out. But these are cells. Bacteria are cells. They just simply diffuse the CO2 out into the environment. The oxygen also enters the same way. Easy. All right. Now I have 2 acetyl-CoAs. Where is all of this happening? Cytoplasm. Very good. The acetyl-CoA, each one, and I have 2 of them, each one turns the cycle on once. Now, last time on Tuesday, if you notice the difference between the 2 charts, on Tuesday I had the 2 cycles like this, if you remember. But today I have them laying right on top of each other. That's why you see everything is multiplied by 2. Everything is multiplied by 2. So I have 2 acetyl-CoAs. These acetyl-CoAs, if you remember, they combine with the oxaloacetate. You gotta remember, it's 2 plus 4 that makes 6. The most common mistake students make, and I don't want you to do that, is they say oxaloacetate becomes acetyl-CoA. I'm like, no. Oh, I meant acetyl-CoA becomes oxaloacetate. No. Because neither one of them is right. It's 2 plus 4 equals 6. So oxaloacetate, 4, combines with acetyl-CoA, 2, to make the 6 carbon citrate. Remember that, please. My mnemonic starts from citrate. So this is kind of like my start point. Can I add some syrup for my oatmeal? Now, when I challenge you to draw this, you remember the mnemonic, can I add some syrup for my oatmeal? But when you go write it, don't write, can I add some syrup for my oatmeal? No, write C for can, I for isocitrate, and then A. You're gonna write the first letter from the mnemonic. And then you have to remember that the first C is citrate. The I is isocitrate. The A is alpha-ketoglutarate, and so forth. Then you overlay it with the number 665, a group of 5 fours. Remember that? Always starting from citrate. So citrate is the 6, is the first 6. Isocitrate is the second 6. 665, that means alpha-ketoglutarate is 5, and so forth. And then you remember, every time the number goes down, and it did right here, that means I am releasing CO2, that means I'm also making NADH. Every time I make CO2, I make NADH, but I would not say it the other way because I would be wrong. Okay, here it is again. 5 to 4. I lost the carbon, made NADH. Between the two S sounding words, I am making ATP by SLP. I'm telling you, the tricks, the clues work and they help you. And you'll be amazed how much of this you already know without even attempting it. You'll see. You go home tonight and attempt this, you'll get about at least 50% of it on the first run. All right, at fumarate, what am I making? FADH2. What word do I remember between fumarate and malate? Boring. There's nothing going on. Nothing that you need to worry about. What do I remember between malate and oxaloacetate? I go back to first grade and I remember MNO, my alphabetical order. And that's how it works. Alright? Did we lose carbon? Did we lose carbon? No, but we did make NADH. That's why you can't say it the other way. You always have to say, every time I lose a carbon, I make NADH, but you cannot say it the other way. So at this point, how many NADHs do I have? Total NADHs. 10. Tell me where they're at. Break them down. 2 in the glycolysis. Good. 2 pyruvate oxidation. Good.
6.
And 6 in the Krebs cycle. There's your 10. Very good. How many FADH2s do we have? 2. Where? Krebs cycle. Location? Oh, cytoplasm. Good. Nice. Yeah.
Just to make sure that, but in the eukaryotic cell, it'd be in the mitochondrial wall.
Oh, you stole my question. I'm about to ask that question. Watch this. FADH2 in bacteria, where is it made? In the cytoplasm. But where is it made in eukaryotes? Which part of the mitochondria? Inner what? You're an identical clone to my 7 o'clock class. It's in the matrix. It's in the mitochondrial matrix. Look over here. The mitochondria. Look over here, please. The mitochondria has how many membranes? 2 membranes. Here we go. I'm going to draw the mitochondria. I am not a very good artist, so forgive me. I'm going to draw the other membrane, okay? Everybody good? I just killed you. This is not possible. This will kill you. Go back to your gen bio. Tell me.
Like a sister.
Yeah. Nobody stopped me. Nobody stopped me. Then you just let me kill you. This is deadly for you. You can't have that. Your inner membrane of the mitochondria is a folded structure. It looks like this. If you remember from your gen bio, I hope you do. Ooh, that, just insisting on hurting you there. All right. There it is. That's how you draw it. The way I drew it before, nah, somebody should have stopped me. This increases the surface area when you're folding something. It covers more ground because the complexes are located in the inner membrane of the mitochondria. The 4 complexes and the ATP synthase. Well, you have enough space to have another one, and another one, and another one, another one, another one, another one, another one, another one. If you only had this you won't have enough space to have a lot of these complexes. So surface area for maximum efficiency. On top of that, you need this space. This space is very important. Why? Because that's where the hydrogen is gonna go. When the complexes pump hydrogen, that's where the hydrogen is gonna go. That's not enough space for the hydrogen to go to. This is not right. Your membrane has to be folded. Now, but that's important for oxidative phosphorylation. But what was my question? Where does FADH2, where is that made? That means, where does the Krebs cycle take place? It takes place here. This is the matrix, the mitochondrial matrix. This is the outer membrane of the mitochondria. This is the inner membrane of the mitochondria. And this is the inner mitochondrial space. This is where the hydrogens go, the space. But where the Krebs cycle is taking place is here, in the mitochondrial matrix. All right. All right, that's it. So at this point, I have 10 NADHs and how many FADH2s? 2. Very good. All right. All the 10 NADHs, all 10 of them, are going to go to which complex? Complex 1. The FADH2 will go to complex 2. How can you tell? 2 and 2, get it? All right. FADH2 goes to complex 2. You can make a song out of it. How's that? So the NADH will go to complex 1 and give complex 1 what? The electrons. Good. What's complex 1 gonna do? How is it gonna react to the electrons? It's gonna pump hydrogen into that space. So even this one has that space. Okay, so complex 1 is pumping hydrogen. Now, complex 1 has to give the electrons to complex 3. Oh, look at this. Complex 1 and complex 3. Here it is. Look at that. Here they are. Here's complex 1, complex 2, complex 3. Complex 4 over there. Here's ATP synthase over there. I love this classroom right? When you guys were walking in, that's what I was looking for. Who is going to be my complex 1? And she came and sat down and then, oh, there it is. But the weird thing is this. Complex 1 wants to give electrons to complex 3. But complex 1 refuses to move. And then we ask complex 3, say no. Can you move? No. So nobody wants to move. But I have to give the electrons to complex 3. So somebody has to move, and it's ubiquinone. Ubiquinone is the relay system between 1 and 3. Because the complexes are in the membrane and they're not moving. Complex 1, 2, 3, and 4, along with ATP synthase, they don't go anywhere. They're sitting like this. I'm not going to. You want the electrons? Yeah, come and get them. I'm not going. So, watch this. NADH gives her electrons. So NADH gave her the electrons. What happens to her? She opens up and she pumps hydrogen. She's done with the electrons. Will she give the electrons to complex 3? Nope. She's above that. She's going to give it to ubiquinone. All right, give them. I'll take them for you. Thank you. There you go. What happens to her? She opens up a channel, pumps hydrogen. Am I right? Yeah.
So
Ubiquinone.
which one is that, the green one?
It's the Q. Yeah, the green one. So ubiquinone has a very boring job.
It's just
It goes like this. Watch. That's it. Takes the electrons from 1 to 3. That's the life of a ubiquinone. And then it can get as exciting as this. Watch this now. From time to time, ubiquinone will take the electrons from 2 and give it to 3. When? When FADH2 delivers the electrons. Nice catch. So if NADH is delivering the electrons,
It's one.
the electrons are going from 1 to ubiquinone to 3. Sounds good? When FADH2 is delivering, it's from 2 to ubiquinone to 3. That's as exciting as it's gonna get for ubiquinone. Yeah.
So then after those three, it pumps hydrogen out?
So she pumps hydrogen. So now, so far, 1 and 3 will pump hydrogen. Remember something, 2 never pumps hydrogen. You better be careful of that. Yeah.
What does that do for this, like the cell?
Hang in there. Hang in. And now, you think if she can't move over there, you think she's gonna move all the way over? She doesn't move. Does she move? Complex 4? No. So there has to be a relay system between 3 and 4. Who is that? Cytochrome C. Now I'm going to pretend I'm not ubiquinone. I am now cytochrome C. Thank you. I'll take it for you. Here you go. The electron. Now cytochrome C has a very boring life. Cytochrome C, that's all it does. At least ubiquinone has a choice, right? Between 1 and 3 and 2 and 3. But cytochrome C, it's always going to be between 3 and 4, 3 and 4, 3 and 4. That's all it does. What's going to happen to 4? She will pump hydrogen. So the ones that pump hydrogen are 1, 3, and 4. Does 2 pump hydrogen?
No.
Never does she pump hydrogen. Okay, now watch this. Now the hydrogen is here. We'll hang on to that. The electrons from 4 in anaerobic cellular respiration, she now has a potential choice. Watch, look, between carbonate, sulfate, and nitrate. You catching that? So you're gonna turn around and let me do this. Carbonate, sulfate, and nitrate, because we're working with nitrate because he's closer to her. You're gonna turn around and give it to nitrate. There you go. He is the final electron acceptor in our example here today. Because he's the last one to take the electron. That's this part right here. In other bacteria, he wouldn't be there, maybe carbonate is there. In a different bacteria, they both wouldn't be there, maybe sulfate is there. You know, the bacteria that produces that kind of like the egg smell. When you're driving by, you know, what is that smell? It's the sulfate one. All right. Don't forget about that guy over there. Who is he? He is Sleepyhead. Remember Sleepyhead? We gotta wake him up. How do we wake him up? Here's your answer. How do we wake him up? The only way to wake him up is to take these little hydrogen ions and fire it through him. That'll wake him up. That's exactly what's happening here. And that's why you pump the hydrogens there. You're gonna take the hydrogen and you're gonna literally fire it right through. It has to go through him. Only then will he wake up. Wake up to do what? To do this reaction. What is the name of this reaction? Chemiosmosis. Chemiosmosis.
Okay, so my question is, so for glucose, so starting from group 4, it gets into glycolysis.
From here?
Yeah.
Yeah.
So it has the carbon, the hydrogen, and the oxygen.
Even when it enters the cytoplasm, it will still be like that.
So it has all that, and then when it gets to glucose and then glycolysis, it like kind of breaks them up a little bit.
Mm-hmm.
And then the pyruvate oxidation
Yeah.
adds oxygen or takes it away?
No. There's no oxygen involved here.
Okay.
No, it's just the name oxidation means I'm breaking it.
So it breaks it.
Just break it. It's this. It's glucose to pyruvate, right? Then acetyl-CoA.
But one, but pyruvate if you're gonna get rid of it.
Why do we add pyruvate?
If you wanna get rid of it later.
No, this is making the pyruvate,
Yeah.
which then tells you you have to get rid of it to keep glycolysis moving. So you're gonna get rid of it for, number one, to keep glycolysis moving. Number two, it still has harnessed energy. Listen to me, please. Listen to me, please. It still has harnessed energy that you're going to release in the Krebs cycle, right? This is part of the harnessed energy. When you make NADH, where did that come from? From the harnessed energy that's still in pyruvate, that is now in acetyl-CoA. You're releasing the energy in the bonds, in the electrons, in the hydrogen, storing it in NADH for delivery to the to the electron transport chain. By the time this Krebs cycle is over, right, there's no more pyruvate, no more acetyl-CoA. All the energy that you started out with is either in the 4 ATPs that you made here and here, or in the trucks. Now you have to use the energy in the trucks to make ATP. So you're now gonna send the electrons through the electron transport chain to activate the hydrogen, pumping of the hydrogen, to fill the space, to wake him up. And we fire the hydrogen through ATP synthase. ATP synthase is the enzyme. What is it making? ATP. How do you know? It's called ATP synthase. I am making ATP. It's in the name, right? So the name of this process is chemiosmosis. What is the name of this process? Electron transport chain. What's the name of both of them together? Oxidative phosphorylation. Electron transport chain plus chemiosmosis is your oxidative phosphorylation. How many total ATPs do we make from the 10 NADHs? 30. 30, because each NADH makes 3 ATPs. How many total ATPs do I make from the 2 FADH2s? 4. Listen to this question. How many total ATPs do I make by oxidative phosphorylation? 34. How many do I make by substrate level phosphorylation, net gain? 4. How many do I make total? 38 maximum yield. Say that 10 times and you'll have it. Meaning everything I said. And you can do it. Yeah, it's not that bad. Questions before I go on to fermentation?
Is the main difference between FADH, or just like NAD to FAD, does FAD hold 2 electrons?
Yeah, they both hold 2 electrons and 2 hydrogens. Yeah.
Okay, they both.
To reduce, you're gonna add 2 electrons and 2 hydrogens in both of them.
In both.
Yeah. Now in one, and I don't want to get into the detail, but in NADH, it actually, it takes 2 electrons and 2 hydrogen, but it makes NADH plus H. Yeah, you can look at the chemistry behind it there, but I won't test you.
So the more ATP we make, the more acidic gonna be in the cytoplasm because of the hydrogen that we pump it in.
You could say that, or the more electrons you deliver, oh, that's very good. The more electrons you deliver here, right, the more acidic this environment becomes. Because H plus, that's hydrogen ion concentration. That will drop the pH. So the way I drew it here, this pH will be lower than this pH. But as it comes back, I think it will level out, right? Because you're gonna just abolish the concentration gradient. So the idea is, typically what people do is they talk about this here. When you have a lot of hydrogen here versus here, that's gonna show you the difference in the pH. I won't ask you that question. I'm mean, but not mean. Okay. Let's go on to this one. And I'm gonna warn you about this. You're gonna get it wrong in about 10 minutes. We'll see. Let me see if I'm right or not. Because I was right before, earlier today. Listen to me. These are the possible final electron acceptors. If you're a facultative anaerobe, for example, you have the pick of choice. But which one will it prefer? Oxygen. A facultative anaerobe final electron acceptor will be oxygen if it's doing what? Aerobic cellular respiration. That's why this is there as a possible final electron acceptor. Okay, what if oxygen is not there? Then it's going to choose one of the three, either sulfate, carbonate, or nitrate. But what will it be doing? Anaerobic cellular respiration. Okay, is there another choice? Yes, and that is an organic molecule. When you are fermenting, and this is the one that some students forget about, that when something is fermenting, there's still a final electron acceptor. See, when they think about final electron acceptor, they're waiting to see the complexes and the ubiquinone and the cytochrome C and well, no, the final electron acceptor of fermentation is an organic molecule. It doesn't have to go through the complexes. It can go directly to an organic molecule in fermentation. For us, that would be lactic acid. So technically speaking, lactic acid is the one that's finally taking the electrons, right? And during fermentation. So that's an organic molecule. So this is the one that students forget. That there is, at the end of fermentation, there's an organic molecule that's accepting the electron that becomes, in our case, lactic acid. So please remember that. All right, one of the final slides is what happens if there is no oxygen or there's no anaerobic cellular respiration, then it's fermentation. So the same events happen in glycolysis, exactly the same. You get to pyruvate, yeah. You ask the question, is there oxygen? No. Is there carbonate? No. Sulfate, nitrate? No. Then I can only ferment. Because I don't care how I do it. I have to do what to the pyruvate? Get rid of it. For what purpose? To keep glycolysis moving. Now listen to this part. And I need your attention because if you don't listen to it, you're going to be confused. There's another reason why I have to get rid of pyruvate. Besides the fact, and they both have to do with keeping the glycolysis moving. To keep glycolysis moving, two things have to happen. You have to get rid of the pyruvate. We talked about that already. But in fermentation, you also have to keep a constant supply of NAD+. Now you have two problems. Problem number one, you want to keep glycolysis moving? Yeah, you better have empty trucks. If you run out of these, and you can imagine, watch, if I run out of these, I hope you agree, glycolysis shuts down. And that would be a bad thing. But at the same time, the problem number two, you have to get rid of pyruvate. And in fermentation, to get rid of pyruvate, you have to reduce it. It's opposite pyruvate oxidation. In pyruvate oxidation, you're taking the electrons and the carbon out of pyruvate and making it acetyl-CoA. But not here. You have to actually give it electrons and hydrogen. And you're like, wait a minute. I just loaded my electrons. Watch. I just loaded my electrons to make pyruvate, thinking I'm going places. the oxidative phosphorylation. But surprise, I'm not going anywhere. This is my analogy of this. Watch this, and it'll make sense. You go rent a U-Haul. Why? Because you just bought a new home. You pull in your U-Haul into your driveway, you load your furniture. Sounds good? You now have a loaded truck sitting in your driveway, and you get into it ready to go to your new address. Right before you pull out of your driveway, your real estate agent calls you. And she's like, yeah, you know that new house that you just bought? Yeah, it's not ready yet. You can't get it yet. There's something wrong, whatever. You didn't do the paperwork right. I don't know. Something is wrong. Oh, but I just loaded my furniture. Well, then unload them. Load them, unload them. Watch this. Load them, unload them. Load them, unload them. That means if I keep doing that, it means I will always have an unloaded truck. That's the whole idea. In fermentation, what are you doing? Besides getting rid of pyruvate, you're also going to have a constant supply of empty trucks. How? Well, to ferment the pyruvate, you got to get electrons. Where are you going to get them from? The truck. It's amazing how your cell, God, nature, whatever, figured this out. If we would all sit as a group trying to think of how do we solve this problem, we might not come up with this. You got two problems, one combined solution. Problem number one, you have to get rid of pyruvate, and to get rid of pyruvate, you need electrons. Problem number two, you have to have empty trucks to keep glycolysis moving. Solution, yeah? You know the electrons that you put on the truck? Yeah, take them off. Give them to pyruvate. That will reduce the pyruvate, yeah? And you'll also have an empty truck. Beautiful, beautiful solution. Hopefully you're impressed too. So you will always have a constant supply of this while you're getting rid of this. The goal for this is to keep glycolysis moving. This will shut down if one of two things happen. If pyruvate builds up, it will shut it down through negative feedback inhibition. If you lose this, it will shut it down because you won't be able to go past this step. So the solution is combine both problems with a single solution. And we call that solution fermentation. That's that solution. This is the solution. Ferment the pyruvate. Now we ferment, so that's what this guy is showing you. The two NADHs that you make here, you're actually using them. So don't make this mistake. The two NADHs that you make here will not make ATP because they're going to unload the electron here. They're going to go back to empty trucks. So these two will not go to complex 1. You got to be careful of that. So now, what are you going to make with this pyruvate reduction? It depends on who you are. If you're like me and you, humans, we're going to ferment the pyruvate to lactic acid. We ferment to lactic acid. We do this and only this. Some bacteria are like that too. Some bacteria are exactly like us. We call them homolactic. Some bacteria are actually more like yeast. They make ethanol and CO2. In yeast, we use the ethanol from yeast for alcohol, for wine and beer.
Would it be cool if we could make our own wine?
Huh?
Wouldn't it cool?
Yeah, but not from bacteria. Bring the yeast, we'll have a party. But not from I wouldn't drink that, not from bacteria. You got ethanol and CO2 from yeast. CO2 is what we use for bread, for making bread, for bread to rise, right? Some bacteria do exactly like what yeast does. They're called alcoholic fermenters. Homolactic means I only make lactic acid. If I'm making ethanol, I am an alcoholic fermenter. Then you got some that say, I don't know which one to make. Let me just make both of them. This one right here. Heterolactic fermenter makes both of them. Ethanol and lactic acid. By the way, this is a much longer list than I'm showing you. Thank God I stopped here. I would have stopped here, but we actually do 2 labs that require you to know these 2. And they're coming up real soon. One of the labs, we're gonna look for this. And what is that? That's pyruvate fermenting to 2,3-butanediol. And then another test in the same lab will be looking for this. Pyruvate fermenting into a mixture of acids. Watch this. A mixture of acids. So we call this 2,3-butanediol fermentation. We call this one mixed acid fermentation. Write it down for now, and we'll talk about it in the lab. To test for mixed acid fermentation, we use methyl red. You catching it now? Here's right away it tells you, oh, I can use it to remember. Mixed acid, methyl red. Get it? Mixed acid, methyl red.
That's the indicator.
That's the indicator that we're going to use to test your unknown. If it ferments this way or not. So you're about to get your unknown real soon. And you're gonna have to do multiple tests on it to try to figure out what it is. One of the tests will be this one. Does it do mixed acid fermentation or not? And you're gonna use methyl red to test for that. What about for this one? There are 2 people's names and they're not easy names. Vocus proscure. So we just call it VP. The VP test. And we'll talk more about it in the lab.
I have a
Yeah.
question. So if it doesn't make any ATP, because I remember in the chart that you showed us at the beginning, they still make 2, so where does that
They make
come
2 from a net of 2 from here. These ATPs will still be made. I'm talking about the NADHs.
Those ones.
The NADHs, they're gonna be consumed during fermentation. So it's like your furniture. Where's your furniture going? Nowhere.
Yeah.
Because you just unloaded them, put them back in your home.
So there's still 2 ATPs from.
You still have a net of 2. And that's what you're gonna survive on. And that's why you wanna keep glycolysis moving. While it's fermenting, you're still getting some ATP, not from the NADH, just these ATPs. What I'm saying is the NADH normally goes to complex 1 to make more ATP, right? Not these 2 NADHs. Because they're going to be consumed during the fermentation. That's a beautiful question on an exam. Hopefully you can tell.
So the organic molecule that you said is the final electron acceptor in the fermentation gonna be pyruvate?
No. Well, it
Because-
depends. I don't want to get into the chemical pathways of this. It's technically the molecule right before the ethanol. You see what I mean? But we're just going to call it the ethanol. You see? It's the molecule right before the lactic acid. So there, in some cases, there's a step between pyruvate and the ethanol. There's one more chemical step. And it's technically, it's that one that's getting the electron. So don't worry about the details. You're just gonna call it an organic molecule. Whether it's pyruvate or the other molecule or that molecule, doesn't matter. They're all gonna be organic. Just call it organic molecule. Unless you want me to get into the detail. Yeah, you want me to? Okay, next class. I'll add it on the slide, just for you. All right. You wanna get into the detail? Look it up. Look at it. All right, you notice something that's in common to all of them? CO2. Do you agree? The only one that's not producing CO2 is which one? The lactic acid. No, nice question. Nice question on the exam. Yeah.
Is that why, like, if you, something with lactic acid and cramps, if you have a cramp, then you can-
Usually cramps is more like like ions, like potassium and things, deficiencies of ions and things like that, usually. Lactic acid might cause more like damage to the muscles, and that's what would typically give you the pain you feel in your muscles after an exercise. I feel pain just standing here. Fermentation is my friend, right? I'm fermenting just standing here. Go ahead.
Just to add to her question, that's like a common fallacy that the reason why you're sore is because of lactic acid, but as soon as the activity ends and you can breathe in oxygen, the lactic acid gets converted back to pyruvate, and that's not the real reason why. Like the muscle damage and cellular breakdown is the reason why you actually have soreness.
The full story of that is this. What you have to do is you have to do what's called a cool down routine.
Right.
So let's say you run for 5 miles, which I would never understand. Anyways, you run for 5 miles. You don't run to exhaustion. You don't run to the point where, I'm done. No. You have to do like maybe 10 minutes before exhaustion so that you can run slower, walk fast, walk slowly, and then stop. What you're doing is, what you're saying, it keeps the circulation moving, your blood moving. So what's going to happen is the blood will pick up the lactic acid from your muscles. And then you're still doing some kind of activity. You didn't just stop. Because if you just stop, then the lactic acid will stay in your muscles. That's not what you want. You want to do a cool down routine, so you're using your blood moving through your blood vessels as a vacuum cleaner of lactic acid. Picks up the lactic acid, yeah? And then all the blood in your body goes through your liver. It goes to your liver and throws it in there. Your liver cells are going to convert the lactic acid back to glucose. And that's the best way to avoid most of the ouch that you feel after an exercise. Will you be able to avoid all of it? No, but at least most of it. Now, the more you exercise and the more it's like a routine for you, you don't feel that anymore. And if I start exercising tonight, I'm going to feel the pain tomorrow. I can tell you, I'm going to feel the pain tomorrow. But if I keep pushing it, you become very efficient. Number one, very efficient at using oxygen. To the point where you might not even ferment at all. Even during like the end of your exercise, you're still using, I would think of marathon runners. These guys are amazing. They're amazing. But they weren't born like that. They got up to that level, right? They can run 26 miles with no problem at all while I'm watching them in bed, right? So, for me, I can't do that, not yet, but I can if I keep training and practicing. So the ideal thing to do is to get rid of the lactic acid is to do a cool down routine. And every exercise and every trainer will tell you, you have to do a cool down routine. You stretch first to avoid hurting yourself, but you cool down to get the lactic acid moved out of your muscles. Okay, one final slide. This you do not need to know, meaning remember or memorize. This is called amphibolism. Let me try to spell it here for you. Amphibolism. Amphibolism. This is my way, or the fancy word for saying the interconnectedness of things. Everything is interconnected. That is absolutely true. You only saw a very small portion of what actually happens in the cell. And even this is kind of like some kind of summary of all the events. If you want to see all the networks of chemical reactions, it will blow your mind away. But what is amphibolism? Amphibolism reminds me of this. I don't know if you've ever heard this phrase, Grand Central Station. Have you ever heard of that? You know what that is? Usually, Grand Central Station is in downtown, usually. What is that? That's a train station, right? That all the trains go into and all the trains come out of. And it's usually somewhere like in the middle of Chicago or something, or Manhattan, New York. It's in the middle of downtown where all the trains come in and all the trains come out. All the trains come in, all the trains come out. Here it is, this guy, acetyl-CoA. Okay, it will share it with this guy too. So these two are like Grand Central Station. All the arrows come in to acetyl-CoA and pyruvate, and all the arrows come out. So let's say you eat some sugar. Okay, here, eat sugar. You come down this way and you get to acetyl-CoA. We've done that already, right? And then the cell says, okay, we got acetyl-CoA. Yeah, okay, what are we gonna do, guys? I don't know. What does he want? What does the cell want? It wants energy. Okay then, Krebs cycle, oxidative phosphorylation, give him the energy. So once you make acetyl-CoA, a decision will be made. He needs ATP, then go this way, make ATP. Right? Versus this. I keep eating the sugar. So I'm making a lot of ATP. And then I keep eating the sugar. I get to a point where, okay, what does he want? He doesn't want ATP anymore. We made a lot of ATP. He keeps eating the sugar. So we made a lot of ATP. So what do we do now? Does he need something else? No, he doesn't. So what do we do? Store it as fat. You're going to store it as fat and then cry for a couple of weeks. Because once it goes there, it's very difficult to go the other way. So that's why they tell you, stop eating sugar. Don't eat too much sugar. You're going to get fat. And a lot of people go, what? Sugar? Fat? How does sugar turn into fat? There it is. Through amphibolism. Grand Central Station with acetyl-CoA, I can make anything. You want an amino acid? It can be made through the Krebs cycle. You should see the Krebs cycle. We just talked about, can I add some syrup for my oatmeal, right? You should see what each one of them can do. Besides it going through a circle like that, what else? You're going to have arrows coming up. One of the arrows takes you, for example, to histidine, alanine, and arginine. Hey, you want to make histidine, alanine, arginine come out of the Krebs cycle and go that way. Glycine and asparagine, okay, come out of the cycle and go this way. You should see what it looks like. From the Krebs cycle, I can produce almost all of the amino acids. And the other ones that I need to make can come out of some other things. So the interconnectedness of things, that's amphibolism. With acetyl-CoA, I can make sugar again. And that's called gluconeogenesis, the formation of new sugar. If I go this way, I can make sugar instead of breaking it down this way. Blue arrows are catabolic. Red arrows are anabolic. You don't need to memorize this. What we need to know is that all the chemical reactions in your cells are interconnected, with some things being very important. Acetyl-CoA, when you break down fatty acids, so let's say you do get up off the couch and you do exercise and you start burning fat reserves, you're gonna break down the fat into acetyl-CoA. Look what, you don't need to know this, but it's an interesting part. Let's say you got a fatty acid that's 16 carbons long. So the fatty acid is made up of carbon, CH, 16 carbons long. Look what beta oxidation is gonna do. Beta oxidation is gonna take the 16 carbon fatty acid, and chop it 2 at a time. Chop 2 carbons, 2 carbons, 2 carbons. Chop it at 2 carbons at a time. What is that? Acetyl-CoA. It takes the 16 carbon fatty acid and chops 2 carbons at a time, because each 2 carbon is a acetyl-CoA. So now you can think, from one fatty acid, I can really run the Krebs cycle. Do you agree? 8 times. You catching that? From 16 carbon fatty acid, if I chop it 2 carbons at a time, I make 8 of these. Am I right or not? That means I can run the Krebs cycle 8 times. And now you can sit down if you want to and figure out how many ATPs you can get out of that. You can get a lot more ATP out of a fatty acid than you can out of a sugar. Because the sugar only runs the cycle twice. Each glucose only runs it twice. But 116 carbon fatty acid will run it 8 times. You can tell it'll make a lot more ATP. You don't need to know that part. Yeah.
So is that saying that we can use all 4 macromolecules and turn all 4 into
Say?
acetyl? Is that saying we could turn all 4 macromolecules into acetyl-CoA?
We could turn all of them.
Yeah.
Into that,
Is
yes.
that what it's saying?
Yeah, look at it. You're gonna find a pathway to this somehow. Whether
So why is it someone who has a bunch of fat stored, why can they not stop eating and their body just use the fat that's stored?
you're asking me that? Are you trying to say something?
That's not
We're
the
waiting for you to figure it out.
first.
We're waiting for you to figure it out. Figure it out. You'll be a millionaire. Just remember me. Yeah.
Isn't it called ketosis though after like 2 days of like starting?
Yeah. That's another thing. Yeah.
That's,
Okay.
yeah. You have to have like 5% carbs.
Is this impressive or what?
Really
I hope you're enjoying this. All right. Let's go.